Okay, this is question 3 of the WJEC Physics Unit 1 AS exam of May 2016. We're now going to talk about question 3. And we have a graph here of the spectral intensity of two different stars. And the question is asking us to confirm that Wien's displacement law is valid for the stars. Well, we need to look at our formula and data sheet, and we need to find the equation for Wien's displacement law. Wien's displacement law is given as lambda max, that's the peak wavelength, equals capital W t to minus 1. Now, if we refer to our data sheet, we're told that capital W is the Wien constant. It has that value there. Okay. So what we're going to do for this question is we're going to take the data from the graph for the two stars and hopefully show that the peak wavelength from the equation is the same as the peak wavelength given from the graph. So let's start with series A. Okay. Lambda max, the peak wavelength, is the Wien constant, which is, if you look it up here, it is 2.90 times 10 to the power of minus 3. Okay. And we're going to t to the minus 1 just means divide by t, so divided by the temperature of series A, which is 10,000 Kelvin, and we're going to get an answer of 2.9 times 10 to the power of minus 7 meters. Now, this wavelength axis here is in nanometers, so if we convert this to nanometers, we would see that it's going to be 290 nanometers. Now, if we look at our graph, and we go to series A, the peak wavelength is there, and if we go down to the x-axis, it roughly lines up about there, which I would say is about 290. So for series A, the Wien displacement law clearly works. We're going to do the same thing with canopus, which is the second half of the question. So same process. And I think laying your worker here is really important. It's telling the examiner which calculation goes with which star. It's very clear for the examiner to see. So lambda max equals Wien's constant, 290 times 10 to the power of minus 3. And the temperature of canopus is 7250. And that comes out to be, we use our calculators, so 2.9 times 10 to the power of minus 3 divided by 7250 is 4 times 10 to the power of minus 7 meters. Again, converted to nanometers gives you 400 nanometers. And if we've got a graph, the peak wavelength is there, which lines up with 400. So clearly we can see from calculation that these two stars follow the Wien displacement law. So on to part 2 of the question. Astronomers state that one of the stars appears bluer than the other. Explain how the spectra support the statement and which star would appear bluer. Well, blue light has a shorter wavelength than red light. So if we look at the stars, we would expect the stars with the longer peak wavelength would appear bluer. Now if you look at the graph, the peak wavelength for series A is shorter wavelength, which indicates more bluer than the canopus star. So the first answer we're going to write down is state which star would appear bluer. So we say series A would appear bluer. Yeah, that's the first mark. And explain. Well, because we can say that the bluer light has a shorter wavelength than redder light. The peak wavelength for series A is shorter than the peak wavelength for canopus. So because the peak wavelength for series A is shorter than the peak wavelength for canopus, and bluer light has a shorter wavelength. Now, plate B part I. The radius of canopus is 4.97 times 10 to the 10 meters, and we're told the radius of Sirius A as well. Show that the luminosity of canopus is approximately 500 times the luminosity of Sirius A. Well, there's a few ways to do this. The way I'm going to do it involves ratios. There are other methods, but I'm going to show you how to use the ratio method. If we look at our formula sheet, to work out the luminosity, the equation we're going to use is capital P equals the area, and that's called a sigma, and that refers to Stephan's constant, T to the power of 4. Now, we're told on the front that Stephan's constant is this number here. Okay. Now it's going to tell us the luminosity of each star, and what we're going to do is calculate the luminosity of each star, and hopefully we can see that the luminosity of canopus will be 500 times greater than the luminosity of Sirius A. Okay. So the way I'm going to do it is I'm going to do luminosity of canopus divided by the luminosity of Sirius A equals, and we're also subbing this equation here for each star. So, area sigma T to the 4 divided by area sigma T to the 4. Now here is the surface area of each star. Now to work out the surface area of a sphere, it's 4 pi r squared. So equals 4 pi. The radius of canopus is 4.97 times 10 to the power of 10 meters. That's just the area. Times by the sigma, which is Stephan's constant. So 5.67 times 10 to the minus 8. Times by the temperature of canopus, which we look back to our graph, and canopus we're told is 7,250 kelvins to the power of 4. And we divide all that by the same calculation but for Sirius A. So 4 pi, the radius of Sirius A is 1.19 times 10 to the power of 9 squared, times by Stephan's constant, 5.67 times 10 to the power of minus 8, times by the temperature of Sirius A, which is 10,000 Kelvin. Now at this stage, we can make things a lot easier for ourselves by doing some cancellation. We've got 4 pi divided by 4 pi, we cancel out. Stephan's constant and Stephan's constant also cancel out. So the equation becomes a little bit more simpler to calculate now. And we just use our calculator. So 4.97 times 10 to the power of 10 squared times by 7250 to the power of 4. 4. And we get an answer of 6.82 times 10 to the power of 36. Now what I like to do is I store these numbers in my calculator. So if you press your shift, then STO stands for store, and we'll store it in letter A. So now whenever I use A, that number is always stored in letter A. And we do the same calculation on the bottom. So 1.19 times 10 to the power of 9 squared times by 10,000 to the power of 4 equals over 1.42 say times 10 to the power of 34. Again, I'm going to store that into B. Now do alpha A divided by alpha B gives you 481, which is approximately equal to 500, which he wanted is approximately 500, which is what he wanted us to find out. It's quite a lot of work there for 4 marks, but you can make it easy for yourself by doing the cancelling. Calculate the intensity of the radiation reaching the surface of the Earth from Sirius A. And we're told the distance between Sirius A and the Earth is 8.15 times 10 to the 16 meters. Now intensity is defined as power per unit area. So intensity is the power per unit area. Okay, so what we're going to do is work out the power of Sirius A and divide it by the surface area through which the light spreads out, if we assume the light spreading out as a sphere. Okay, so the power of Sirius A is this calculation up here, isn't it? So it's 4 pi times by 1.19 times 10 to the power of 9 squared, that's the area, times by a Stephan's constant, 5.67 times 10 to the power of minus 8, times by the temperature, Sirius A, which is 10,000 and to the power of 4. That gives you the power output of the star Sirius A. And we're going to divide that by the surface area of a sphere at that distance away. So imagine this is the star, then the light is spreading out in all directions. And it's a sphere, so it's all three-dimensional. And the surface area of a sphere is given by 4 pi. The radius of that sphere is the distance between Sirius A and Earth. So 4 pi times by 8.15 times 10 to the power of 16 squared. Again, we can use some cancelling, so 4 pi goes there and there, disappears, and we're left with 1.19 times 10 to the power of 9 squared times by 5.67 times 10 to the power of minus 8, Stephan's constant, times by 10,000 to the power of 4. That's the top row of my numerator of the equation. And we divide that by 8.15 times 10 to the power of 16 squared. Gives me an answer of 1.2 times 10 to the power of minus 7 watts per square metre. Because our power is our watt and our area is meters squared, so watts per square metre. Part 3. The intensity of the radiation reaching Earth's surface from Canopus is less than that from Sirius A, even though Canopus has a greater luminosity than Sirius A. It explains apparent contradiction. Well, even though Canopus has a greater luminosity, it essentially is saying it's appearing dimmer in the sky. Well, this can be explained if Sirius A is a lot closer than Canopus. So Sirius A is closer to Earth than Canopus. That would be the first mark. Okay, that's a statement. We need to explain it. So because the radiation is spread out over a smaller surface area. If you think about this as the star here, that's Sirius A here, and say, for example, if the Earth is closer to Sirius A from Canopus, the radiation from Sirius A is spread out over a smaller surface area. Okay, that was question 3. If you've got any comments or questions, please leave them in the section below.